Um okay, so hello everyone. Welcome to the book club of designing data intensive applications. Currently, we are on the chapter batch processing, and we have been looking at Mapreduce, which is one of the ways to do batch processing. So, last time we looked at how Hadoop uses its distributed file system HDFS and MapReduce jobs on top of it to perform batch processing jobs, right? Um and we looked at some of the basic MapReduce jobs. So today, first I'll give the brief overview of the things that we're going to discuss today, and then we will jump on those things one by one. Um, so whenever we are doing batch processing where we have to process lots of data, we will most often encounter the scenarios of joins and group, right, where we want to join data between two different where we want to join two different kinds of data, like for example in SQL when we have to join data between two different tables, right? Similar things we would need to do in these batch kind of jobs, right? So we will understand what's the difference between joins in a SQL query versus joins that happens in a batch job, and this MapReduce kind of a framework for batch processing, how it performs those joins, right? So uh, since we know MapReduce has map step and reduce step, right? So now joining happens. There are various ways and various algorithms of joining. Either the joining happens on the reducer side, or the joining could happen on the mapper side, right? And we will discuss how these algorithms are different, and when could we use one over the another, right? So then, yeah, so that would be this joins and grouping. Then we will discuss what's the difference between actually Oltp versus Olap versus batch processing, right? Then uh, how this MapReduce kind of batch processing could be used in various applications. So one of the good application could be building search indexes. So that's one thing we could understand, that how search indexes are built through MapReduce, right? Uh, and then basically we will discuss how this Hadoop and batch processing is different from distributed databases, like distributed databases like Olap databases, which are used to perform like Olap kind of queries. So how Hadoop is different from those, right? Because both of them seems like they are used for analytic kinds of data where you want to run where you want to query your data set for large amounts of data, right? So they seem very similar, that Hadoop is also doing something similar, and these distributed databases also do something similar, right? So then exactly what is the difference if they seem so similar? So that will be like, I think that will be the last part of the discussion. Okay. So uh, so starting with the joins and grouping. So before joins and grouping, like a brief overview of MapReduce workflows. So basically a MapReduce job has a mapper step and a reducer step, right? Which finally produces the output. But in most cases, like we would need to, like we saw the example of Unix, right? We had to write various input output workflows to finally perform whatever we wanted to do, right? We used those pipes, and then we had to run those multiple of those commands where one command was using input and another was being, and its output was being used as input of another, and then finally we got what we wanted to do. So similarly in MapReduce, you generally would see that you would have to write workflows where you're writing one MapReduce job, and that MapReduce job is being used as an input of another MapReduce job, right? And like at least in my organization, there are uh, various tools to build those workflows where, like, basically it there could be this scenario that you are you write two MapReduce jobs, and the output of those two jobs serves as the input of another. So basically, you build workflows that wait for this job to finish, wait for this job to finish, take the input of these two, and now uh, do this another MapReduce job, and then this output is the final output, right? So that is something which you will see doing a lot in practical scenarios. So yeah, so that is MapReduce workflows. Okay, now coming to joins and grouping, right? So first, let's see what's the difference between database joins and this batch jobs join. So in database, generally when you query your database and when you have to perform a join, you generally perform the join only on few records, right? You are looking for, let's say you're looking for this user ID in the user IDs table, and then find his friends, let's say, right, in friends table. So you are looking for that only one particular record. So, and that particular record is generally indexed, so you can look for the indexes in those two tables and get your result, right? So things can happen in memory, and the data set is very small, so it's easier, right? And you can use index for those lookups. But in batch job, whenever you're doing batch processing, then you are not generally looking for just one particular record. You are looking for you are generally performing the join on entire data set. So we will see an example. So let's say, a typical example of what you would be using a badge of for be. So let's say you have user activity events, right, which shows that this user ID has done this activity, and then you have a user database that this user ID has this email and this date of birth. So a typical batch job would look like that. I want to uh, find out by age group what activities are performed, right? And I want to analyze that data, right? So in this case, now I have to join the entire data set. I'm not looking for a particular user or a particular record. I have to join this entire data set, right? So that's why, like, having an index or something like that is not useful, and generally batch processing systems, and this, like in this case HDFS, they don't have any index as such, right? Because you don't need index. You are going to merge the entire data set, right? So so now, yeah, so this was the basic difference, that in your DB, like, you're looking for one record, whereas in batch jobs you have to merge entire data set, so there is no index concept, right? So that is one thing. The other thing is that so basically in this scenario, let's say we have to do this, that for each user activity, we have to find out that what age group it lies in, right? So one simple way we could do this is that for each record, you go to user database and find, like, what age group of that what is the age of that user, and then you have basically then joined these two data, right? So for each user activity you're going to use a database, but I mean, like, in very simple sense, that you are making remote call to this database, right? But then it's not very ideal approach because of few problems. The first problem is that for each record, you would have to go to like your database and make that database call, which would be expensive, right? Second thing is like if your database, if you have not taken a, like if you're not working on a backup of your database, if you are making a call to a real database, then the problem is this database could be constantly changing, right? So basically you won't have a deterministic results. So that's why like a fundamental thing of running any batch processing job is that you have to treat your input as immutable. So to treat your input as immutable, so basically probably the this MapReduce system, or it could be the responsibility of application, that you have to take a snapshot of your database, and that snapshot, you run your batch jobs on the snapshot of the database, right? Because if you're not taking snapshot of your data, if you're running on data that is live, then as you will be running your batch jobs, that data might be changing, and so you will get non-deterministic results. And the same thing we have discussed in the transactions chapter also, that uh, basically that was the problem of read skews, right? That if analytic job is uh, reading the data and that data is changing, then it will face the problem of read skew. So to avoid that problem, you generally take a snapshot of your data, right? So the same thing is repeating here again. So yeah, so now these were the basic fundamentals. So now let's see how we will actually do the joint, right? So first we will discuss the joints that happen on the reducer side. So there were two steps: map, reduce. So now we're talking about the joints which will happen on the reducer side. So in the reducer side joints, basically uh, so basically this I think there is only one approach mentioned. So this sort merge is the approach to join on reducer, and then there is an approach to group by. So we have these join queries and group by queries, right? So now first let's see this join happening on reducer side, and the algorithm is called sort merge join. So basically it's very simple, nothing fancy in this. So the mapper is given the, so basically we had this user activity table and user database, right? So mapper is given the responsibility that for each user ID, like you get the key as the user ID and value as whatever URL he has visited, right? So this is the mapper for user activity, and the mapper for user database would be key will be user ID and value will be its date of birth, right? So this will be done by mapper. Then the other step was shuffle, right? We remember that the next step was shuffle. So shuffle will bring all the related keys to one machine, right? So all the keys with 104 as the key will be brought to this same machine, right? And now the data is on the same machine. So now the reducer has all the data with it related to the same user ID. So now it can perform whatever join it had to perform, right? So basically mapper has done the task of bringing the similar data together, and now reducer is going to perform that actual join, right? So this was this sort merge join, right? So it's happening on reducer, and it is called sort uh, because the mapper, if it wants this framework during the shuffle step, it can also sort the data, and it can sort the data in such a way that like these, let's say, URLs are sorted based on the timestamp, and basically you will see the date of birth as the first, like the data from user database as the first result, and the data from the activity mapper following it, and these results are sorted by timestamp, right? So this thing could be performed by the framework. So it will be sorted, and then the reducer will be merging those sorted results, right? So this was sort merge, right? Any questions in sort merge, Join? Yeah, and basically like this will like, if you look at this picture in the book, so this is also not the entire process. So basically reducer has got this result that for this URL, this is the date of birth, for this URL, this is the date of birth, right? But finally we wanted that for each URL, what is the age group, right? So, and we have not got the final output from this. So basically this output will be served as the input of another MapReduce job, where the key will be the URL and the value will be date of birth, and then the shuffle step will bring all the URLs with the same key to one machine. And now then that reducer will reduce that this URL was viewed by this age group people, right? So it can do the classification and all. So that will be the final output of what we want. So like this is one another example of MapReduce workflows where like was one MapReduce job, and now this input will be used as this output will be used as input of another MapReduce job to get your final data. Right, so this was how you perform the join. Basically like simple in terms of SQL, you had two tables and you wanted to join them. The other thing that we used in SQL kind of databases is group by, right? That uh, group by some particular thing. So let's say uh, if we have some data where we are storing that for each user how many times he has viewed a page, right? We have those logs, and then we want to group by user and do a aggregation on count, right? That's to get how many pages a user has visited in a day, right? So those group by kind of queries that we do in databases, how will we do in batch processing? So uh, so again it's very simple, like mapper. So in the example where you want to get the where you want to group your data by user ID and then get a count of total page views, so your mapper will bring all the logs related to same user ID on one machine, right? So mapper will map your data based on user ID, and shuffle will bring together all the data with that key on one machine, right? And then now whatever we had to do in this case, let's say we have to the sum the page view count, right? So that sum part could be done by the reducer. So whatever aggregation we need to do, count sum, that could be done by the reducer, right? So that was like this joining and grouping uh, on the reducer side. So now one big problem which we could see with this approach is skews, right? That because we are bringing all the similar data with the same key on one machine, we could see the problem of skews, that if one particular key has lots of data, then one machine would have to process that lots of data, right? So, and probably that data could not even fit on that machine, or it has to process that lots of data, right? So how do we handle skews, right? So this is, so now let's understand one by one that how will we handle the skews in the joins, and then how we will handle the skews in grouping. So because we have just discussed grouping, let's first discuss how to handle skews in grouping. I think Does anyone wants to answer uh, how will we handle skews in group by data where one key has lots of data? Yeah, to me, like it seems like quite obvious that basically you can partition your data, right? And like how MapReduce works. So for each of the machine is processing some subset of data, and then finally you are grouping the data all together. So for example, for a particular user id, one user id was uh, using the system a lot and he has lots of logs, right? And you want to get the count, right? So you can partition data by his user ID on multiple machines, let's say on 5 machines, right? So each machine will do the count. So the group by will happen individually on each machine. So each machine will do the count. And then those 5 machines will then later aggregate their results to get the overall count, right? So grouping is simpler. You just partition the data on machines and then finally do the aggregation again, right? Uh, the yeah the the thing to understand, which is little more complex, is joins, right? So in joins, basically we are joining the data from two data sets, right? So let's say those two data sets are two tables, although they might not exactly be tables, like those are like data encoded in those file systems, but you have two different kind of data set, right? So let's say one is left side and another is right side, right? So one of the ways you can handle skews to perform join is that so basically you partition the data from one side of the table, and from the other side of table you send all the records from that side of the table, right? And so basically, like let's say the example that we have a table of user activity and user session locations, right? So user activity is giving that for each user ID he has performed this activity, and user session location is giving me that this user ID has performed uh, has opened the session at this location, right? So now let's say I want to get this data that at what locations various activities were performed, right? So I want to join these two tables. So basically I can partition the user location data. I can do a partition on multiple machines, and all the records for that user ID, all the records in user activity will be copied to all those nodes which has user location partitioned. So now for because I have like user location is partitioned and user activities replicated to all the machines. So now for each user location, I can find out that what were the activities he performed in that location, right? So that's how I can like partition the data if it is skewed and still perform the joins. Any questions here?
I kind of got confused like between grouping and joins right now.
Mhm.
Like in the grouping also we have partitioning, right? Basically you have a key and like a hotkey, and on that hotkey you will group the data and send it to multiple reducers.
Yeah.
And in this also we are doing the same thing.
Yeah. Mhm. So
So
the
yeah.
the fundamental difference between grouping and join is that your grouping happens only on one data set, right? Only on one table you would be performing group by, right? Whereas joins happen on two data sets. right?
Okay, so like if I have two data sets, then there will be join, right? And if grouping is there, then obviously I'll have just one data set and be performing grouping on that just one data set.
Yeah.
Okay, okay, got
So
it. Yeah.
then like on one data set, if you have to group, right? So basically your data for one key cannot fit on one machine, right? Or you cannot, like it's too expensive to put the data on one machine because all the processing will happen on one machine. So what you're doing in grouping is you are splitting the data, you are partitioning the data. Each machine is doing whatever aggregation it had to do on that data, and then finally again those now records have been grouped and that aggregation has been saved, which is then sent to another job which then does the final aggregation, right?
Mm-hmm.
So this is how grouping could be done. But in case of joins, because you have two tables, so it's a bit complicated that now how do you split the data, right? Because you have data from two tables. So we are saying that we will split the data from only one table and then copy all the records for that key from the other table on all the partitions. And now whatever logic you have to perform on the join table, you can then perform that logic.
Okay, thanks.
So this was joins and grouping. Uh, now coming to map side joins. So the disadvantage of reducer side joins is uh, that basically all this process of extracting the keys, then sorting the keys, and then moving the data to those machines, uh, in this process, like lots of time data has been written to files at various steps, and this entire process could be quite slow, right? uh, because like you have to join that entire data set and you have to do all these operations, so it could be a bit expensive, right? So to make this process fast, we can use map side joins, but the thing about map side joins is you need to have some assumptions about some your input data. Like if you know the size of your input data, then you can optimize using the map side joins. So one of the optimization is broadcast hash join. So in broadcast hash join, the assumption, the use case is that when you are joining two data set, one data set is very large and one data set is very small, right? So in this case, what we will do is that whatever small data set that we have, we will broadcast that small data set to all the machines. And then on each of those machines, we can quickly perform the join by like this small data set will be stored as hash table in memory on all of those machines. And then you can quickly perform the join on all of those machines, right? So this is broadcast hash join. So again, the assumption is that one of the data set should be very small, and that data set will be used as a broadcast, right? Uh, so, and then one interesting thing which was mentioned, like in this book, was that even if your data set is not small enough that it can fit in memory, still using the concept of page cache in operating system, right? You can perform this broadcast hash join, uh, right? And this data could be still stored on disk where the frequently used parts of your data set will be stored in page cache by your operating system, right? And so basically it will be, so basically because your most frequent parts of data will be stored in memory in page cache by OS, so it will have same fast performance as doing a in-memory lookup, right? So this was one another thing, that it's not mandatory that your small data set should fit in memory, even if it's a bit larger, as long as like some parts of the data is repeatedly used and they're stored in OS page cache and they can be accessed from memory, we can still use broadcast hash join, right? uh, the other approach is partitioned hash join. So so um, in this partition hash join, basically we are uh, this input data uh, is partitioned uh, onto various machines, and it's sorted. And so like the use case of this is that your data should be sorted. So to perform this partition hash join, your data should be sorted. So if your data is sorted, so basically you partition your data onto multiple machines. So let's say in case of user ID example, let's say you can partition the data by the last digit of user ID. So this way your data will be partitioned onto total 10 machines, right? And so now, because the data is sorted, oh wait, sorry, I think I am incorrect here. The sorting was used for map side merge join. Okay, this is a different partitioned hash join. If input to map side is partitioned in some way, it can fit in memory, and above hash join approach could be applied. Okay, yeah. So in this, um, uh, basically
In
we are splitting the data.
Yeah, oh no, I was just saying in this partition hash join, both the data sets are partitioned in similar way. So like in this, they gave an example where user ID ending with 3, if you partition both your data set like activity and the user information with, let's say with user ID ending with 3, then we can have all the data from user information which is ending with user ID 3, ending with 3, and activity also where user ID is ending with 3, and then they can be joined easily.
Yeah, right.
Yeah, I have a question here. But why we do consider this join as map side join? Yeah, as for me, it's also reduce side join because we need to shuffle both tables on left and right on the right side, and then join them on reducer side. What do you think about?
Mhm. Um, so, like I don't know exactly, but in the book it's mentioned that so in map side joins there is no reducer step. So basically, all these steps are being performed in the map step. So
Oh, I see.
Yeah,
So
I think what would happen is like if there was some MapReduce job in which the partitioning already happened by a certain key, and then the next MapReduce job is going to consume it. I think there this can be used.
yeah, yeah, right. So
yeah, I agree. So if we already has on disk one of table partitioned, yeah. So
yeah,
divided to in partitions, then we in another job we can use just simply read appropriate partition and join, yeah.
yeah, yeah, right.
Ah,
Yeah.
thank you.
And like so similar is this map side merge join, where so in reduce side merge join, we were first like we were the data was sorted and it was merged. So similar case here, that data is sorted, and then the sorted data, even though it cannot fit in memory, so the mapper basically it will look at the keys in both the tables because they are sorted, so it can like merge them, right? So it will look from the top in the ascending order. The keys are sorted in both the tables, so it can merge them, right? And again, uh, this is also like your data will be sorted. Basically, if you are doing it as in a workflow where one MapReduce job outputted your data in sorted way, and now then this MapReduce job could use map side merge join because your data is already sorted, so it can do those joins faster using map side merge. So the other difference between reduce side joints and map side joints was that in reduce side joints, like your data would be final outputted, your data would be partitioned and sorted by join key, right? It is doing that shuffling and sorting your data. But in map side join, like all those steps are removed, your data will remain same as whatever, like the order of data will remain same as whatever the input was. So either, so that's why to efficiently perform this map reduce joins, either your data should be small or either your data should be already sorted, because by itself map side join won't do any of these heavy lifting tasks, and it assumes that the input has already done that heavy lifting, and then it can do the joins faster because the input data is in some expected format. So yeah, that's the map side join. And then the other thing was mentioned was that, so these assumptions about the data in map side joins, they are stored in some metadata store, which is called H catalog and Hive meta store. So that's yep. So that's it. Uh, does anyone has anyone any experience in using any of these? Do you want to share any more insights or any other information, or should we move on? Yeah, in my case, I have just used this broadcast uh, hash join. So basically, yeah, like I have not used MapReduce, but a similar framework to MapReduce, which I used in my organization. So there, if I have to perform the join, so there you can write SQL kind of queries. And there I have seen that if you have to perform joins to optimize your joins, if you know, so that SQL like syntax, it supports a broadcast keyword which you can use if your data set is small. So basically in your join query, you will specify this broadcast keyword, and then using that keyword, it will then assume that whatever is the data set after that keyword is small, and then it will try to perform the join efficiently.
Yeah, I can add a couple of words about broadcast join as well. There is one more strategy for broadcast. I mean broadcast nested loop join. If we have one small data set, yeah, and big data set, and in case if we don't have equity condition, yeah, but condition like similar to SQL like something, yeah, we can use broadcast nested loop, not broadcast hash join, but broadcast nested loop join. If we don't have equity condition, yeah, there is one. Just want to say that there is one more strategy for broadcast nested loop. Spark uses it as example. Yeah.
So it's not hash. Then what did you say instead of hash? What?
It's broadcast just
Hmm.
array, and we can use this type of join when we cannot use equity. Like if we
Right,
have conditional ID1 equals ID2, yeah, we can use broadcast hash join. But if we have condition like ID1 like ID2 or something
yeah,
or something like it, we cannot use hash join, yeah, because we don't have equity. We
right.
cannot build hash map and probe, but we can still use broadcast, but we will have something like nested loop, and Spark call it broadcast nested loop join.
Okay, got it. Yeah. So yeah, so the broadcasting part will remain same, that the data set is small, but because we are not, so hash, the advantage of hash is that it gives you exact lookup, right?
Yeah,
Now, in this case of like kind of scenario, it's not exact lookup. So you cannot use hash map. So
yeah,
you will use some other data structure which will give you like
yeah,
similar data, but yeah, but it's
yeah,
same
yeah.
thing. Yeah. Okay, that's good to know. Thanks. Okay, so yeah. Uh, so now the difference between OLTP, OLAP, and batch. So OLTP we know, right? Online transaction processing systems, where mainly we are looking for just one particular record, and we are generally, these are online systems, so they're expected to be very fast, and you're looking for one particular record, right? Olap, online analytic processing systems, where you are using these data systems for analytic kind of query. So you are running it on a large data set, and uh, and here you are not looking for a particular one record, but you are doing some aggregations and all on your entire data set, right? So like, give me the count of all the users uh, with this property and all. So here, like, you are not looking for one particular record, like you're looking in your entire data set, right? So that's Olap. Batch, it's like similar to Olap, that you are you are like scanning those large portions of your data and then doing some work on top of that data. Uh, but we will see later that there are some differences between OLAP and batch processing jobs, and like they are not exactly similar. There are differences. So I think this part was explained later in this book, but I think let's discuss that first because it's related to this. So yeah, so this is the part, right? Hadoop versus distributed databases. These distributed databases, which we use for OLAP, they're also called massively parallel processing data systems, right? And they're basically used for OLAP kind of jobs. So what's the exact difference between these Hadoop kind of batch processing systems and these distributed databases? So we will discuss three differences: the difference in storage between these two kind of data systems, the difference in processing, and the difference in fault tolerance, right? So let's go one by one. So the difference in storage. So uh, generally these OLAP kind of databases, right? Because they are databases, they require you to store data in very structured way in a particular model, right? You have to define the schema of your data, you have to define what are the columns, and then you are storing your data in that form, right? So basically, before storing your data, you have to do careful data modeling of your data. Whereas the thing with these batch kind of a system, uh, like Hadoop, that these are distributed file systems, which are just sequence of bytes, right? Where you can use any data model and encoding format, and then you can just dump any data you want, right? So you don't have to first think about that I have to model the data. You can dump your data, and then later, whatever batch jobs you want to run, you can run your batch jobs on that. So this similar, and it's similar idea to data warehousing. If few people have heard about data warehousing, where like you are bringing data from various parts of your organization and dumping it in one place, and then later figuring out what to do with the data. So right now you just dump your data because you don't know in future how that data could be useful, and then later like you figure out like how you can improve your systems and how you can use your data to actually analyze and build better systems, right? And this is also called like sushi principle, right? So like raw data is better, so because, right? So and then like there is this another term, ETL processing, right? Extract, transform, load. So these batch Hadoop kind of data systems are also used for ETL processing, where like raw data is dumped, right? You extract the data from your raw raw data, which is stored in distributed file system. Then you transform it. So you transform it by running some Mapreduce jobs to make sense out of that data, and then you load it. So basically you store that data. Now this transformed data is like useful to you. It has some useful information, so you will load that data in some in some MPP kind of database, because now your data is in more organized and structured way. After you have run your MapReduce job, you have organized your data in a better way, and then you can probably use it in MPP. So that's the load part, that now you have loaded your data in a more easier to query uh, data system, right? uh, so and so what we're saying is that in these Hadoop kind of system also data modeling still happens, but data modeling happens at a later stage, right? At the data collection stage, you are just dumping everything on distributed file system, and then later you are modeling it in whatever way you want to do, right? So this was the difference in storage. Then there is a difference in processing. So generally these Olap kind of databases for massive parallel processing, they prefer to keep their data in memory, right? And so basically they only support SQL kind of queries to query your data. So they can optimize your database for those kind of queries, so they can return the results very fast, and the order in which they return the results is few seconds to few minutes, right? Whereas in batch jobs, in Hadoop kind of jobs, your jobs could run for a very long time, like they could run for hours, right? uh, so and the Hadoop kind of a system, it generally tends to write your output or intermediate outputs on disk. And the reason why it does that is, there are two reasons. First, that it tends to be more fault tolerant. So we will discuss in the next section. But to be more fault tolerant, you have to write things on disk, right? If you are storing things in memory, then if fault occurs, you will lose your data in memory, right? Uh, so it writes the disk things in file. And the other reason is that generally the intermediate outputs or things it is producing are generally expected to be much larger, that they cannot fit in memory. So that's the another reason that it's eager to spill data to disk. Then the other difference is, while MPP kind of systems only supported SQL kind of queries, right? But here in batch jobs, you can write your any code you want, any custom code. So in your mapper and reducer, like you can write anything you want, so you can do whatever you want to do, right? So in this way, these systems are more flexible, and in fact, there has been other systems built on Hadoop kind of system, which uses uh, HDFS as a storage layer, and then building various other kind of processing system. And those are like either MapReduce or like Hive and all, even implement like SQL kind of query execution, where you can write SQL kind of queries and it will convert it to MapReduce kind of job and output it, right? So so that's the difference in the processing of these two things, right?
And
Then
one
Mhm,
more thing is, so even though we have differentiated, right, that MPP and Hadoop as a not MPP, uh, but the Hive, there are two modes for running a Hive. Hive is a data warehouse inside Hadoop. So
mhm,
you can also run Hive as an MPP.
mhm, mhm,
So generally, if you submit any Hive queries, what happens is the query optimizer creates a MapReduce job,
mhm,
and then it sends that MapReduce job to the resource manager, and then it schedules where to run this job and all that. But
mhm,
in the MPP, there are some dedicated nodes which are like constantly always running. Like you don't have to reserve a capacity like you have to do in a normal Hive.
mhm,
So that way the queries run faster. They are not as fast as true MPP databases like Snowflake and all, but they are very comparable and very fast.
mhm,
And the other thing that we have seen here, right? We see this MPP like prefer to keep data in memory.
mhm,
It's not true for all, because the new databases that whatever are coming, right? So if you take an example of Snowflake, the Snowflake data resides in S3, and it does not keep them in its own file system or anything. It just uses the S3 file system, and whenever it needs to process a data, instead of the way normally we think, right, we will keep the data in memory. Instead of the memory, whenever the uh, whatever is the frequently accessed data, it keeps them in its own local storage.
mhm.
And that also the I mean the Snowflake also removes the third point, right? Like they have a separate file system for MPP and Hadoop. So if you are using like Snowflake, you can also run queries, since it is on a S3 data, you can also run queries on it. The- And you can also do a background loading of the data in S3 at the same time.
I see. So yeah, so like, can we say that the lines between MPP and Hadoop are like kind of blurring, because the advantages that Hadoop, the MPP would be providing, Hadoop kind of system, people are building system on top of it that will provide those advantages. Like if you want expressive SQL kind of queries, then there have been things built on top of it which will give you those functionalities. Similarly, whatever are the advantages of Hadoop, like if your data is spilling and cannot fit in memory, it writes to disk. So MPP kind of systems are also trying to do that if you need those functionality.
So the Snowflake exactly does that, but Teradata and all, which are also kind of an MPP
Mm,
systems, they have their own separate architecture. Like they don't use any distributed file system or anything.
mhm, mhm,
So, um, I mean, the nowadays, like lot of mid-sized companies who earlier went on Hadoop, they went away from Hadoop and going into these solutions like Redshift, BigQuery, or Snowflake. The reason was the maintaining a Hadoop cluster is a investment,
mhm,
right? Because it's a big thing. So rather than that, if you just opt for an MPP database like or these SaaS solutions, it becomes easier. So so the these MPP databases are not trying to solve what Hadoop does, but what Hive does. They have taken that part.
Okay, okay, okay.
So mostly, most of the places where who have gone on to the Hadoop thing, majority of the use cases were as a data warehouse, and that data warehouse is done. I mean, in Snowflake, uh, it gives a exactly similar functionality like Hive, like you can run queries and all. Also, it is scalable. Plus, it has it stores the data in a different format, like a columnar format,
Mhm.
and every column has its own file in it, so the queries become faster and all. So they have the similar things also exist in Hadoop, uh, but the majority of the MPP databases go for this columnar file formats.
Mm.
Because if you take a look at the analytics queries, right,
Mhm.
most of the data scientists are much like all the reporting people, their queries are mostly like, give me the max of this, give me the average of this, uh, what is the like deviation of a particular column and all that. So those queries are very beautifully fast served by the columnar structures.
Mhm.
So that's why they went with the columnar data storage.
Right. Okay. That's really good information. Yeah, and like, have you worked on snowflakes? Have you actually worked with snowflakes?
Yeah, so we are working on Snowflake, but to be honest, you don't get to learn as much you get to learn in Hadoop. The reason is Snowflake is fully managed; it's as a service. So, and only thing you need is a SQL. Like when you query a data, like the way you query data in Teradata or the Hadoop or Snowflake doesn't make any difference. It's like just the SQL. And in Snowflake, the when I say like there is not much to learn about how Snowflake was, the reason is Snowflake takes care of all those different things. Like in
Okay.
Hadoop, you have the ability, right? You can create a table and say my table will be in a Parquet format, or my table will be ORC or Avro. But in Snowflake, you don't have those features. Mostly, um, they store it in their own way. I mean, you can store that, but generally people don't do that. So it is, you just query it. Like my interaction with the Snowflakes in last 2 years was, I just wrote queries in it. Like uh, they have they have a thing called virtual warehouse. Is basically when like you can buy your compute on demand.
Mm-hmm.
So let's say in our organization there are 100 teams, so they gave a warehouse to every team, and the warehouse is nothing but how many compute resources you need. So our team has, for example, a 16 node warehouse. So, and the beauty of that is when you run a query, it starts the warehouse, runs your queries, and if nobody's running a query for 15 minutes, it shuts down that warehouse.
Mm-hmm.
So it's as true as saying like you are not using, if you're not using it, not so. That gives a lot of advantages and marketing points, right? Because you can save money and all that. uh, but it is good. Like I haven't seen any problem with even Hive and all. uh, but the Snowflake seems like, since it takes care of all these things, people love it.
Mm. And so like what so like Hive is also like similar that you can write SQL kind of queries on top of it, right? So how like what are the differences you have felt in using Hive versus Snowflakes? Because there also you don't have to do all this kind of that you're writing your mapper reducer, right? You just write SQL kind of queries and then Hive.
No difference. It's like only thing is the way you write UDFs and all, right? So in Hive, if you want to create your own functions, you create a UDF. So you have to write that UDF class and send it to this Hive. The similar things were not there before in Snowflake, but nowadays they have. But in terms of all the standard SQL functions, all of them are exactly like that. And both are like NC SQL style.
Mhm.
So whatever the style you write in SQL, it's like it's a drop-in replacement. Like your queries don't change, except for there are very few tricky things that I found which were very frustrating with the Snowflake, where it is not good with the inline queries and the way MySQL queries work easily, the Hive queries work easily. It does not take care of few things, but those are very edge cases. But
Mhm.
most of the things are like almost similar. Your query will almost run same in the Snowflake.
And like you mentioned, like the advantage of Snowflakes is that it's kind of managed service, so you don't have to worry about assigning the clusters and all those things.
Yeah.
I believe that is something you have to do in Hive, right?
Yes, so in Hive, the what happens in the Hive is when you run inside a Hadoop cluster, there is a quota thing that you have to give,
Mhm.
and then the scheduler decides what how, because let's say your Hadoop is can run 10,000 jobs at a time. So
Mhm.
in ETL job, if it is running, you don't want to hamper the SQL queries that maybe come after, right? If there is a big ETL going on, all the queries will. So in that case, what Hadoop does is it solves the problem using that yarn, and inside the yarn, you create quotas for different people. So you can say, okay, ETL team has 20% of the cluster. The
Mhm.
analytics team has like 50% of the cluster,
Mhm.
and Hadoop does that job really good, in the sense if the cluster is empty and if the people are whoever are running query, they needs the full power, it will try to run the job on almost all of the nodes. It will try to use the 100% capacity.
Mhm.
And when the priority client, like whoever owns the 50%, if his query comes in, it kills the remaining jobs and makes space for them. So that way it takes care of those things. But doing all these things, I mean, in practically was constantly a problem inside our organization, uh, because this housekeeping work is significant to assign quotas and to run these jobs, and your jobs fail because they were we were using the unused capacity. So that was a little bit pain point.
And then how would Snowflake solve it? Because like again, like at any time, if you have limited amount of resources and you have to
So
ban.
yeah, so there is no limit in Snowflake. So they say for example, let's assume there is a we have a petabytes of data, right? And there are two teams. So for these two teams, we will not share their resources. What a Snowflake admin will do is, it will say, okay, uh, let's say your team, I will give you a 100 node warehouse, and for my team, it will give 25 node warehouse, and they are entirely different. So this 100 nodes warehouse doesn't have to do anything with the 25 node warehouse. Both can run at the same time.
Yeah, I
And
understand, but the problem is then it will be more expensive, right? Because like similar thing you can do. I mean, if you want, you can do in this Hadoop kind of system also, right? That
yeah,
if you have so many
so
machines with you to spare, then you can give everyone different kind of machines. But that's the problem that they were trying to solve, that making the
yeah,
best use of those machines.
correct. So the Snowflake solves it by saying that if there is no query running on your warehouse for 15 minutes, it shuts down the warehouse entirely.
Okay.
So it achieves a cost saving on that part. But even if there is a few queries running, let's say you have a 100 node warehouse, and your query is just running on one node, your 100 node warehouse will be spinning, like the meter is going on for that.
Hmm.
But as soon as that is done, it shuts down. If there is no query running, it will shut down the whole thing, and startup and shutdown is pretty fast in it, like you don't see much difference in there.
Okay, okay. Hmm. Okay, got it.
Yeah.
Yeah, that was very good information. Thank you so much.
No.
Yeah, so then the third part, fault tolerance. So in MPP kind of systems, if in let's say you were running a query and it's something failed in between, then they generally tend to abort the entire query, and they will either retry by themselves or the user has to retry that query. And retrying is actually not a big problem because MPP kind of queries, they tend to run for a few seconds or few minutes, so that's why it's not very expensive compared to this MapReduce kind of systems where your queries would be running for hours. And like if something fails in between for a for a job that you were running for 1 hour, and if something fails it restarts, then like it will be very frustrating, right? So these MapReduce kind of systems, they can tolerate fault, and also because they write their intermediate states on disk, so they can retry their failed part, they can retry and rerun that failed job, right? uh, so this was then very interesting thing mentioned. So the question here is that so yeah, MapReduce is made fault tolerant, that if there are failures, then you won't retry the entire thing. It will rerun from there, right? But generally, if we see system failures, right, that the node crashing, that does not happen so often, right? So why do we need to build such kind of system? Why was MapReduce built to be fault intolerant? Like in those situations, in those rare situations where a machine fails, we could have been done by just retrying the entire job. Because if we are saying that the machines don't fail so often, which is practically true, right? They don't happen so they don't fail so often. So then why was uh, what was the fundamental use case that MapReduce was made fault tolerant? So the so basically again, so this comes down to resource sharing. So when Google built the MapReduce, uh, they wanted to run MapReduce jobs on the same machines which were serving their online production services. So imagine those same machines, they are being used to serve online user queries and any other stuff, and the same machines will be used for bad jobs as well. So they want to make optimum use of their machines, right? So for example, let's say I have some machines reserved to serve Gmail, right? And I see that Gmail usage in particular region, let's say in US at nights, it's very less, right? So those machines which I have reserved the capacity to run Gmail, they have lots of free resources at night in PST, right? In PST night, let's say in any region at night time, it won't have heavy usage, right? So they wanted to make best use case of their machines, because anyways their machines are running, right? They are taking up electricity and all those resources, right? So they, so that's why their this fundamental goal was that they want to run those bad jobs on those online production machines, where these online services will have higher priority and these bad jobs will have lower priority. So if this online request comes higher priority, then these bad jobs will be terminated, they will be killed, and that high priority thing will be done. And it's fine to kill these jobs because like these are bad jobs where no one is immediately waiting for the response, right? So now if a system is killing these bad jobs, so now the frequency of failure has increased much more, right? So now it's not just the machine failures which are happening, but your entire process which is running on top of it, it also has the ability to kill your bad jobs if a higher priority job comes. So that was the main reason that these MapReduce jobs were made to be fault tolerant, because of this increasingly likelihood of failures because of this reason. Uh,
And I think they like this philosophy is still continuing in the Google Cloud. So if you take a look at the what are the costs related to a servers, right? So if you want to create a one compute servers inside a Google Cloud, which is a dedicated, which is going to be always up and running, and if you compare that with a preemptive VM, in that case the preemptive VM is in on Google Cloud, and this was like 3 years ago. The preemptive VM is almost 80% cheaper than the dedicated VM. So
mhm,
Google says basically if you can write your app in such a way that even if we move your machine here and there, even if we shut it down and start it somewhere else, then you can have a huge cost saving.
mhm,
So when we wrote a job, like it was a POC though,
mhm,
so we tried to make use of that fact.
mhm.
It's like 80% cheaper than the dedicated VM.
Yeah, yeah, no, yeah, it's like quite, yeah, it's very interesting thing to do, and like it could save a company a lot of money and resources if they can like make this best use of resources. So yeah, so this was about fault tolerance. Yeah, so these were the differences between Hadoop and distributed databases, right? So we discussed the storage difference, processing difference, and the fault tolerance difference. Uh, yeah, I think that was pretty much it for today. I mean, there was briefly mentioned about how search indexes could be built by Mapreduce, right? And so basically, uh, the basic fundamental idea behind building a search index is that you have your documents and those documents have words, right? And now for each word you create a posting list. So that posting list is the list of document IDs that that word appears in, right? So then basically if someone is searching for that particular word, then this posting list will be looked up so that you can return the documents in which that word appears, right? So this is like basic fundamental thing how search indexes are built. Like there are other complexities around it, but the fundamental is this. So to build these kind of search indexes, like you have, let's say, bunch of documents and you want to create an index on top of it, so you can run a batch job. So that batch job, it will on each document it will do whatever processing it needs to do. So the mappers will kind of partition your initial data set in whatever way you have uh, told the mapper code to be, and then the reducer will build the index out of that partition, right? So so that's how like this map reduce kind of a system was used to build search indexes initially in Google. Right now they use some different kind of a system, but yeah, that was it. And so generally these indexes are read only and immutable. So if a document changes, then like one option would be like to run these indexing jobs periodically after some frequent interval of time, and then replacing whatever new index you have built, right? And this is okay in kind of search kind of scenarios, right? Because uh, like a Google, like a search system, search engine, it never guarantees that its index is totally up to date, right? There could have been a new web page which would have come up, or there could have been some changes in a web page, but your search index might still not have indexed that page, right? Although it would be good to have those latencies as low as possible between the data change and building the index, so that your index is as fresh as possible. But like it's not like a utmost requirement from a index, right? So that's why like one simple approach could be that you are periodically running your indexing jobs. So if those document changes, those are captured by those rerunning of the indexing, and then you are basically updating your index. Or the other approach could be that you are building your indexes incrementally, where whenever there are any changes, then you are uh, saving those new changes and then merging and compacting them with your existing index. So yeah, so this was like how search indexes are could be built using MapReduce. Uh, then the other thing which was mentioned was that storing the output of your batch jobs in DB. So uh, like we discussed in ETL, right? Extract, transform, and load. So you extract your raw data, you transform it, and then basically you might want to save the output of your batch jobs in some DB, so that now you can query that data faster, right? So let's say your batch processing job gave you the list of related products related to a particular product, right? So now you have got your output of your batch job. Now you want to save that in a DB so that you can show it quickly to a user that for this product, these are the related products, right? So this kind of saving your data into the database, like if you think about in a naive way where like as part of your MapReduce code, you will be making a call to the DB APIs where as you get each record, you will be saving that record into the DB. Like as soon as your MapReduce reducer gets the record and you save that record in your DB by making an API call to your cloud DB or something. If you write it like that, there could be a lot of problems, right? So we should not do that. First thing is that making network calls for each record will be expensive. And then because these batch processing jobs run concurrently, so like your database could be overwhelmed because there will be a lot of writes happening to your database, right? And also, as we have discussed, that MapReduce jobs, they themselves have this thing about all or nothing. Like either they will fail completely and remove all the intermediate outputs they have, or they will produce your entire data, entire output. Like they will never produce incomplete or intermediate data, right? But in if as part of your MapReduce, if you're also making a call to external DB, then like let's say if some part of the job has failed and it is retried, then you could be making a call to your DB multiple times, which might have some side effect in some situations, right? So that's why so the better solution, if you want to save your output, like don't save your output in the middle. Wait for the batch job to produce its final output files. Then those output files could be, these output files could be used as your data, which could be loaded into your database. And there could be various ways, but yeah, so use that final output file to save the data. So yeah, I think then there was little bit about how these batch jobs compare to Unix, right? So in some ways there are a lot of similarities. So like this HDFS act as a file system, right? In Unix, when we write these Unix jobs, they read and write from the file system or from standard input output. So that HDFS is that file system, right? And then whatever functions and processes you run in Unix, let's say you were running that sort process. So your MapReduce is that processing framework, right? So in that way, these philosophies are similar. And as we discussed in Unix also, that input is always treated as immutable, right? You don't modify your input and you should not have any side effects. So same thing, right? Same thing, that your input should be immutable, and there are a lot of advantages of having immutable input. Is that if you were running your MapReduce job and your MapReduce job had some buggy code, then your input is never modified. So you can fix your MapReduce job and you can again run it with the correct code, right? Because you still have your input. Then the other thing is that the same input can be run to provide different insights, right? So some team could be using same input to extract some data. Some team could be using that same input to extract some data, right? So that same input could be used at multiple places. So because of all those things, like having those advantages of having immutable input, so the same philosophy lies in Unix as well as in this Hadoop kind of system, right? Yeah, I think that was the other thing. The differences which was mentioned in Unix and Hadoop is that so in Unix, the input is basically a raw input text file, right? And you have to do a lot of that input parsing. So the example which we saw initially, there, like you have to, the file contain those sentences and you have to get the seventh word which was important to you, right? So that input parsing you have to do, which could be like a little bit expensive. In Hadoop, generally you are storing data in little more structure, so it is not as structured as your MPP kind of database, but it is also not as raw as like Unix kind of data. So you are storing your database in Avro or Parquet like schema. So that's one difference between Unix and Hadoop. Yeah, that's pretty much it. Okay.
Hey Abhi, can you make me presenter like host before you drop off?
Yeah. Okay, so that's it for this. I'll stop recording. Thank you, everyone.
Thank you, Abhishek. Yeah.
Thank you very much.
Hey Abhi, are you there?
Yes, I'm there.
Okay. Yeah, if you are continuing for next session also, that's fine. But like, yeah.
I have made you host.
Okay, thank you.